Good afternoon, dear guests, scholars, and engineers. I'm Xiong Longfei from Kingsoft office. I'm very honored to discuss the technical application in the field of PDF with you through this conference. Kingsoft office is a software company founded in 1988 and headquartered in China. Main products are WPS Office and WPS Docs. We have over 500 million monthly active users and over 1.2 million installs on PC, Mac, Android, iOS device. These users often face a document element in common. It's table. As one of the most common data representation formats, the table has taken a significant place in documents because of its capability of representing the wealth of information. In daily life, we may deal with all kinds of tables, some of which have become pictures. Some are scanned to PDFs, which can only be viewed but not edited. How to turn an uneditable table into editable state has always been a hot research in academia and industry. As an office software company, our users have diverse needs for tables. There are various deformed and polluted tables that need to be identified and restored. So we have invested a lot of resources to deal with table restoration in complex scenes. And I will show you our latest working in this presentation. Today, I will introduce the following 6 key parts to you, hoping to give you a basic understanding of our work. Firstly, the background and challenging of table restoration in complex scenes. Secondly, the overall flowchart of restoring non-standard table in PDF or images. Thirdly, a high recommended table structure extraction method. Fourthly, a well-designed scheme for table restoration. And then a system design and implementation on different platforms. At last, a summary and outlook of our work. In standard PDF, which may be generated by regular software rendering, the table lines, text, and the image objects contained in it may have known coordinates, Unicodes, and even the font type. It's relatively simple to restore a table with original information. On the right side of this slide, the regular table in a scanned PDF seems also easy to process, since the information can be obtained easily by ordinary image processing techniques. The table lines can be obtained through edge detection by using OpenCV library, and the text can be detected and recognized by all kinds of open source OCR toolkits. If you encounter the following problems, like the PDFs or photos which are generated by old scanners or taken by cell phones, might be skewed, blurred, deformed, or may have complex layout, random orientation, or stems, signature, interference. Some may also have shadows and interference from other objects. Let's say coffee stains on papers. Some tables text may have styles and colors and all underlined, bordered. What's more maddening is sometimes you may also see several small tables nested within a larger table. Anyhow, it's incredibly challenging to reconstruct such a complex table from pixel information. In order to handle such tables, we will face the following challenges. For example, how to detect and identify various elements in table, since the table may not only filled by text and images, but also handwriting, signatures, or seals. The page where some tables are located may be deformed. It will cause the table lines text also be deformed. And even the cells will no longer aligned. Because of the deformation and interference mentioned above, it becomes difficult to obtain table lines, remove interference, and confirm cell relationships. When we get all the elements we need, how to assume all the stuff together is also a big problem. And in order to make the table has a better looking, we also need to figure out the font color, font size, font type, and the paragraph information of the text. In order to solve the problems mentioned above, we can use the illustrated technology roadmap shown in the figure. In order to be able to join with in a slide, I only kept the key parts. First, we may do some pre-processing to correct the original document, and the corrected image will be sent to two models. At the same time, the up branch is the non-text detection network, which includes all elements except text. And the bottom branch is the text detection network. Since we need to remove interference from other elements in text detection and recognition. And then we obtain the original table lines by segmentation network, then divide the tables into different types and adopt different restoration strategies, which include cell search, cell relationship calculation. This is because we found it difficult to handle all the types of tables with the same scheme. Finally, we combine the results of text, images, cells to obtain a complex table expression as XML or other format you may need it. The pre-processing part actually includes a bunch of the interference algorithm, such as the removing shadows, removing memorial, improving contrast, and extra. But you can see the solutions in many other articles. Here I only list two most critical pre-processing schemes. The first is perspective correction, which is the key to dealing with the distortion in PDFs produced by mobile phone photography. The core technique is to detect the four vertices of document. And so the deep learning regression network and the technical key lines in the generation of training data. The second is banding correction. We obtain every single character and then calculate a 3D surface, and then achieve the deformation correction of the entire page through remap. It looks simple, but it's a lot of work. This slide shows how we can break down a complex layout into various elements that can be extracted and recognized. The table, text, underline, image, stamp, signature, and so on can be detected by well-designed detection model. As you can see on the right, table area, underline, stems, and all detected with a bounding box, which means we already know the location, coordinates, and the type of the object. The traditional table line extraction algorithm is only useful in oversimplified things, such as table with straight lines and plain backgrounds. However, the real cases would always be complicated. To solve such a dilemma, we adopt a saliency segmentation model, U2Net, to extract both vertical and horizontal table lines. This design will make it easier for us to get the cell vertices through the intersection point later. Here I want to show you the skills of model training. The most important thing is data enhancement. In the production of training data, we used a variety of enhancement methods to expand the generated virtual data and labeled real data by adding background and interference noise and all kinds of transformation like rotating, affine, bending, and color changing. Another trick is using BCE loss and dis loss for joint optimizing in model training. In order to cope with the tables of different scenarios, we divide all tables into three categories: 4-line table, 3-line table, and a wireless table, as shown on the top right, so that target design strategies can be made. As a result, we can obtain better restoration effects from those type of tables. We adopt SE ResNet as classification model. In order to improve the classification accuracy of these tables, we mix segmentation map and edge detection map into classification model. After dividing the row and the column lines of the table, we take the intersection and the possible intersection of the row and column grid lines as potential cell vertices. Endpoints of the lines that are a certain distance away from the table intersection could also be a potential cell vertices. The result of the potential cell vertex can be seen in the figure on the far right. When actually taking pictures, there will be various complex backgrounds and uneven lighting, which cause the results of table line segmentation not that good. And there will be incomplete line segmentation and broken lines. In order to restore the table structure more accurately, we adopt a post-processing. First, denoise the segmentation results by removing isolated short lines and points, and then complete the table lines by a bunch of table line completion algorithm as shown in the figure. And after obtaining a relatively complex table line, we will use a certain strategy to confirm the cell vertices, and then perform cell search by constructing an undirected graph. Then we apply these logic rules to all the cells and finally extract the structure of the table, as shown in figure 4 below. There are many search strategies, one of which can be seen on the right. Text detection in deformed tables faces many challenges. For example, there are deformed text of any shape very densely arranged text, and interference of table lines and the text areas that are difficult to distinguish between horizontal and vertical. In order to solve these problems, we have to design a more suitable text detection network. We embedded a transformer module in the neck of well-known text detection scheme DBNet, which improves the model's ability to obtain contextual semantic information and receptive field coverage, and also make it easier for model to learn deformed features. In addition, by introducing elastic transform data enhancement, the detection effect of the model in curved texture scenarios is improved. The text recognition adopts the most common used CRN scheme, but in order to cope with the text in different kinds of orientations, we have modified it and added a bypass to predict text orientation, which is very helpful for improving the accuracy of text recognition. Of course, the most important thing is still the training data. We labeled a large amount of deformed real text data and produced a lot of simulated text data. This gives us a significant improvement in recognition accuracy. Therefore, data is always the best friend of deep learning model. In order to obtain a better ability to restore text attributes, we designed a series of modules to identify whether it's about font type, paragraph relationship, and the text color, so that the restored table can be better reflect the style and attributes of the original table. In this part, deep learning models and the traditional CV algorithms are combined a lot. None of them can do such a delicate work alone. The entire system has more than 20 models and more than 100 algorithm modules, involving complex resource usage and scheduling processing. So we designed a layered service framework for deployment, as shown on the right. The bottom layer is the hardware and the service deployment platform. The second layer is the inference framework. The third layer is a variety of algorithm capability models, which include deep learning models. The top layer is a scheduling layer, which is used for business process and extra interface. This system supports all kinds of picture input, whether it's scanned PDFs, pictures downloaded from the internet, screenshots, or photos taken by mobile phones. The conversion system can be deployed in the cloud or locally, and the output file formats are rich and varied. It can be regular XLS table file, or a DOC document, or a HTML format. The conversion speed and the QPS under two machine configurations are listed here for reference. It can be seen that it takes about 11 seconds in the CPU environment. And if multi-threading is running, 5 to 15 pages can be processed per minute. Our online service is deployed on the cloud with GPU, taking a 4-card T4 as an example. The conversion speed is 186 pages per minute, and a single page takes 2.8 seconds. It seems to be quite resource intensive, but efficiency improvement is still very obvious compared with human handworking. Here we check out the recognition ability of this system through a series of samples. For this kind of tables with standard horizontal and vertical lines and clear text, many engines might be able to restore it perfectly. Since we can obtain ideal table lines and structure even by traditional image processing. Meanwhile, the texts are also very easy to detect and recognize through all kinds of open source OCR toolkits. What if the table in the nature scene has curvature and uneven lighting? The challenge is much greater, and it's likely that the traditional CV algorithms are already difficult to handle. This scenario already needs a correction and algorithm enhancement, since some of the text can be barely recognized by human eyes. As we can see, the puppy picture on the right was also detected, corrected, and then pasted back into the corresponding cells. Look at this kind of pictures. The difficulty will increase a lot when the table is not facing directly. And obvious, the table on the left is also crooked. The table on the right is not only perspective distorted, but also has different objects in the upper left and the upper right. But in such cases, our restoration effect is still guaranteed. And if we want to know the ultimate ability of this system, we can test it with even worse samples. The samples on the left is not only blurry, but has stamps and signatures. Meanwhile, the table lines are very dense and the texts are very small. As we can see, the restoration is still fine. And even worse, if the table document is smashed into a ball and then expanded, as long as the human eyes can barely recognize the table structure and text is on the right, our system can still handle it. The result is not bad. In conclusion, use our current solution. Tables in scanned PDFs can be recognized and reconstructed by a series of algorithms, whether it's regular or deformed. Benefiting from deep learning techniques, picture from table regain its original and rich information. The entire set of techniques can be relied on cloud or locally with GPU for computing, or with the CPU is also. User experience get a sharp increase because the technique speed up the whole process of reconstructing tables. However, the OCR and the table structure recognition should still be improved, since they are not perfect. Calculation is not only time-consuming, but also resource-consuming. So optimizing work is completely necessary for the future. They are the image reference, and now is the question and answer section. All the questions are welcomed.
I will ask a question. You mentioned something about combining traditional algorithms with deep learning models.
Yeah.
How was that experience? How do you combine these traditional algorithms with the?
In recent years, deep learning techniques are widely used, but they are not 100% perfect. Some of the process or the tasks cannot be handled by deep learning technique. So we use the pre-processing mostly with traditional CV algorithm, and the detection and segmentation task usually use deep learning model. And sometimes we will combine traditional algorithm idea into the model, and throwing training the model has the ability of some of the traditional algorithm.
Okay, thank you. We have one more question, and you might like this question. Is this available in Europe? Because we saw a lot of files from.
It's still not, but our colleagues are working on it. Maybe in recent days, the people in Europe can use it too.
Okay, that's good to know. Any questions? Last chance. If not, then we have a video. That's a 2 minute approximately video which.
It's a demo video. Then you can see the effect. It's a demo website, and here is the input. We can choose from a PDF or an image, and then we upload it to the cloud. This example is a PDF, and the original one in PDF, and after if produced, it will produce a new PDF with how to say deformed format, and the table with colors and attributes can be also produced. This one is with color and curved, and now the result is flat. And this kind of sample is with temps and or handwriting. It's okay with images in the table cells. It can be restored. And this one is maddening with curved paper, and it can be produced perfectly. And this one is with perspective distortion, and then it's this one is the how to say
paper.
Yeah, it's much difficult, but it can be done. And this one is the most maddening. Yes, that's all. Thank you.
So thank you for this presentation.
Thank you.